Okay, let's get started. Really excited to have Rob and Catherine here. Looks like Rob is giving the talk. They work at a quite exciting company, but more importantly, they worked on ConceptNet and what was open mind common sense in the early days and spun it out and really caused it to thrive. So love to hear the topic, and as you know, they're here for the day to chat with us. So thank you so much for coming all the way to Boston, from Boston to enjoy our winter.
Great, thank you, Lauren. All right, I'm getting the idea that I don't have to convince you too hard that knowledge matters, but this is kind of a big claim in NLP right now. And so I want to tell you about our perspective on how to use knowledge in NLP, coming from the ConceptNet project and from Luminoso, the company that we've built out of it. So here are a few ways to think about words in natural language processing. You can think about words as vectors, and this is an idea that goes back to the 90s with latent semantic analysis. It was repopularized very suddenly by Word2Vec and by later follow-ups like Glove. Alternatively, you can think of words as being nodes in a knowledge graph, and that's the WordNet approach. You can see that in DBpedia. You can see that in very highly structured knowledge projects like Psych. You can also consider words to be just a sparsely observed signal that's that you're putting into a machine learning process, and that's for one thing, that's how search generally works, that you're just matching words traditionally, but it's also your input to tools like Focal Wabbit that still are pretty effective today, tools that are maybe not so effective today like LDA, I don't know. But anyway, here are these three different views, and I think there's a lot of interesting things you can do by overlapping them. So ConceptNet, I'm going to say, is focused a lot on overlapping the idea of words as vectors and words as graph nodes, because ConceptNet created this knowledge graph, and I'll show you a little bit about what ConceptNet is in a bit. But also the idea of being able to represent words in this vector space, to be able to represent relationships between them kind of implicitly, that added a lot to the power of ConceptNet. And then you've got other intersections going on here. Like if you've got your vectors and you've got a sparsely observed signal, then you've got something like fast text, which is the Facebook word embedding maker and classifier. And if you've got your sparse observations and you've got your graph nodes, then you've got the kind of thing where you get a whole ton of consultants to make you an ontology. And if you overlap all of these, like if you take ConceptNet and combine it with observations from a particular data set, then that's kind of the approach that we use at Luminoso, of starting with general knowledge, adding in some specific knowledge to make one unified model. So talk a little bit more about word vectors, because that's what a lot of this is going to focus on. Word vectors are great because instead of just looking for exact matches between strings, we're looking for matches in meaning. And so the idea is that if you've got words that are near each other in a vector space, then they're words that are that should be related in meaning. And having this dense vector representation is a really convenient input for machine learning. If you want to do an end-to-end deep learning process, then you can make it one step shallower. You can start with something that you already have and don't have to try and train meanings, train a representation of meaning at the same time that you train everything else. And then the big question is, how do you get this information about what words mean? And that's where we're going to take a step back and talk about open mind and common sense and how we approach this. So we had this project, Open Mind Common Sense, and it was about collecting the information that people know and that computers should know. And so I've been working on this project for a while. Catherine's been working on it for a lot longer. She was there to start the project in like 1999. Here's a picture of what the site looked like around 2007. You could look up a term like soup, and you'd find these natural language facts about it. The relevant terms in the facts would be links, and it would also ask you some questions that were involved in filling in some gaps in its knowledge. And so this was us using word embeddings to do inference in 2007. We just didn't know that was cool at the time. And so we were also, at the time, turning this natural language-focused representation into a more graph-structured representation, and that's ConceptNet.
Rob, sorry,
Yes.
to interrupt.
Yeah.
Are you going to talk more about how you did that inference? to generate the questions, or not really?
I mean, yeah, I can talk a little bit about this. There is so the technique that I published and like presented at AAAI in 2007, I think, was called analogy space. And now I feel bad that I used that name because like there's so much more with analogies we can do now. But it was basically the idea that like you have these word vectors that you can compare, and that if you like say like, okay, so here's this term and I know this thing about it, and here's this term nearby, maybe I should also know this thing about that term. And so if you collected enough evidence of that kind, it would make that potential inference rank highly on here. And it was sometimes right and sometimes wrong, but that made it a great source for asking questions to fill in knowledge. Yeah.
How do you define the relations between two items? Here I see that location relation and
Yeah.
type relation.
Yeah. When OpenMind was started, I wish I had a picture of this. It was just a box that said, like, tell the computer something, like a fact of common sense knowledge. It was like the Google search box.
I was in fact very influenced by the Google
Yeah.
search box,
Yeah.
so much so
Yeah.
that I sort of ripped it off.
Mhm.
And it was just like, there was a box that looked like Google, and there was a button instead of I'm feeling lucky, it said teach the computer. And then we found people entered data in predictable patterns. So they used location relationships, they used part of a lot. And sometimes we would say inspire me, and then it would show a previous relation. Then people would use the same, using priming, they would use the same thing as before. And so that's actually where the initial relations came from, are the templates that people started entering data in.
Yeah, so ConceptNet has a set of about 24 relations. There's some of them in the long tail that I'm like constantly adding or removing or whatever, but there's about these 24 relations, and it's mostly because of the patterns that people used to enter knowledge into OpenMind Common Sense and to find relations that fit those patterns. And now we've added a couple more relations to represent other things that we can get from other sources of data.
Are you still collecting that knowledge?
Yeah, we are not still collecting knowledge from crowdsourcing, and I have a bit to say about that. We are still expanding ConceptNet, but the approach is very different these days because like I feel like there's a lot of linked data we can benefit from and a lot of like good resources, but directly crowdsourcing is a lot harder these days. But I'll get to that in a moment. So here's an example of the kind of stuff that you'd find in ConceptNet right now. So you've got your nodes, you've got labeled relations between them. These nodes can be in different languages, and that's pretty useful because it helps you get a representation that like when you're learning a representation from this, you can learn a representation that works in many different languages. And to get this kind of information started, we took the OpenMind project and the ConceptNet project, and we took it multilingual. This is when we were at MIT. We were working at the Media Lab, and we formed collaborations with groups all over the world to create both crowdsourcing projects and games with a purpose that would collect knowledge in those languages, and that got us started representing common sense in a number of different languages. So some collaborations we had. So generally we worked with groups around the world to get these different languages. We also had a collaboration with Sterling University. They were working on affect sensing, which was the term at the time for now what we would call sentiment analysis pretty much. So they were starting to do that with ConceptNet. And so yeah, these collaborations produced those different interfaces and games, and some of them went on for quite a while. So the data sources in ConceptNet now have gone beyond OpenMind Common Sense because there is a lot of data out there in different forms. And so I would say the three main kinds of data that we represent in ConceptNet are crowdsourced knowledge, data from games with a purpose, and expert resources. So crowdsourcing now, like OpenMind Common Sense, we're not running that anymore. It's hard. But there's like projects out there like Wiktionary, the dictionary version of like Wikipedia, that is still a very successful crowdsourcing project. And all we have to do is be able to parse their data, which is slightly harder than it sounds given the Wikitext format, but very valuable. So that's a place where crowdsourcing still actually provides new content to ConceptNet. And there's other projects out there like DBpedia being just a graph representation of Wikipedia. there's games with a purpose. This is both a general concept and the name of a particular group at CMU that made things like verbosity. They then went on to make Duolingo, and then they became a company that focused on Duolingo. But verbosity was a pretty neat game. It was a taboo-like game where one person gets a word and they have to try and clue it without saying it to the other person using common sense clues. And so that it was designed to collect common sense data, and they shared their data with us. And a lot of that is in ConceptNet. And there's similar things. Nadia.jp was a word game in Japanese that ran until very recently. And PTT Pet Game. So there was this basically this BBS system in Taiwan that like a ton of people used, and there was this game you could play on it involving having virtual pets and like. So our collaborator Yenling Kuo from National Taiwan University made a game on PTT where you could made an extension to this pet thing where you could teach your pets things, and they would teach other pets things, and it's like. I'm still not entirely clear on how it worked, but it collected a lot of knowledge written in traditional Chinese. And then there's all these other expert resources that are linked data that we can connect to now. We got multilingual dictionaries. You've got the open multilingual WordNet. You've got the part of Psych that's open. Recently been looking in the Unicode CLDR. There's just this language data thing that gives you descriptions of all the emoji in a ton of languages, and that's actually pretty useful for language right now. Yeah, so you're asking about like if we are still crowdsourcing, and I would say that we benefited from the golden age of crowdsourcing, which is something that is sadly over. But from in this slightly more than a decade, you could set up a project and get good data from people who just wanted to be part of something. And if you crowdsource now, people expect money for it, like on Mechanical Turk. Because they're being paid these tiny amounts of money for it, you get a lot lower quality. It's not like the motivation is different now. It's just a menial job. And if you set up some kind of altruistic crowdsourcing project, it immediately gets attacked by like 4chan. There was an example of that when there was like a crowdsourcing approach to the Pentagon Shredder project in 2011, where the idea was there was a team that was just crowdsourcing, putting together shredded documents like a giant jigsaw puzzle, and then there was a equally large team of trolls that came in and just started like rearranging everyone's work. I think that was a good sign of the end of the golden age of crowdsourcing. So just a few more specific examples of facts in ConceptNet and where they came from. So I looked up a term that we know a bunch of different things about, like the word sleep, and you can find, you would sleep because you're tired, and that's the kind of fact that we would get from open mind common sense. You could get the fact that sleep is in some way related to rest, and the fact that people used rest as a clue for it in verbosity a lot is a clue to that. Or the fact that the people would use the clue like sleep is not wake, or sleep is the opposite of wake in verbosity, gives you the antonym relation. You can get kind of more, the highly detailed things that you get from WordNet. Sleep is a physiological state. You can get translations from Wiktionary. You can get, we now have this kind of pseudo relation, external URL, which points to the same term in different knowledge bases. And we represent forms of words. Yeah.
So just to make sure I have this right, so it seems like, right, the nodes are words or phrases.
Yep.
The edges are, types in a vocabulary, in a formal vocabulary. And then from the dictionaries, you're using the fact that sometimes they talk about synonyms or forms. You're not using the information in the definition or something.
Sometimes. So when we're parsing Wiktionary, for example, a lot of times the definition is one or two words, in which case we use that directly as a link. This is very often the case when, so Wiktionary is a project to define the words of every language in every language. And so often when you're doing a multilingual definition, it is just giving the synonym in another language. If it's a longer definition than that, one thing we look at is we look for the words that are linked in the definition, because that's the ones that are linked are the ones that are being emphasized as being relevant. And so maybe it's not a synonym relation, but it is at least related in some way. and then sometimes there are specific things like, say like, here's some, here's an explicit list of synonyms and antonyms, here are derived forms of the word, things like that. All right, so that's the kind of data that we've collected over the decades now. And then there's this other thing that's been going on in natural language processing, which is the idea of distributional semantics, that you just take in a whole large body of text and look at words in their context, and you set up a system to predict words from their context or predict context from their words, and then you look at the representation that that system learned, and those are your word embeddings. And this started out happening kind of independently of our approach to NLP, and recently they've merged together because they are both effective in different ways. So the probably the most effective representation here for distributional semantics is the idea of skipgrams, where you train a system to predict words that are, you give it one word out of a sentence, and you ask it to predict what the other words around it are, which sounds backwards, but it really actually works better than the direction you would expect, where you predict the word given the words around it. And that's what powers like word2vec and fast text and all of those things. And so you take a system that's trained like this, and you slice it open, and you get your word embeddings. And so you've learned a representation of words from distributional semantics. The idea that you can learn meanings of words just from the words around them. And this is great, but it's not quite enough. There's knowledge that you're not going to easily get from distributional semantics, because what you're learning is what words have interchangeable contexts, and that's not the same as them having interchangeable meanings. And so here's this little experiment that I ran to highlight that difference. I took some two-word phrases that I can look up, for example, in both ConceptNet and word2vec, like the pre-computed word2vec vectors come with some phrases. And limiting the matches to single words, so I didn't just get the same thing back, I asked, what is the closest word? And if I ask, for example, word2vec about high school, the closest thing to it is elementary. If I ask it about, of course, the closest thing to it is and. If I ask about the Red Sox, it says it's close to the Yankees, which, being from Boston, is, an indication that's like, we need to fix something here. And so ConceptNet can get something that's more of a synonym in most cases, or something that is a generalization instead of just being another example of the same thing. And so this, I think, shows the advantage of having specific information about meaning.
When you say closest ConceptNet,
Yeah.
what does closest mean in ConceptNet?
Right. Yes. So I'm actually yeah, I guess this is slightly out of order because at this point I'm also using the word vectors in ConceptNet. So yeah. So yeah. Yeah.
Is it based on the numberbatch?
Yes. Yes, I'm about to get there. So yeah, so we have these two approaches that I'm presenting as separate, but the punchline is that I'd really rather use both of them at the same time. So if you've got semantic networks, like what ConceptNet traditionally has been, and you've got distributional semantics, and they all have these different advantages and disadvantages. Like, it's definitely an advantage of distributional semantics that all you need is a lot of words instead of having to have specially structured knowledge graphs. An advantage of semantic networks is that it doesn't matter if your knowledge is rare as long as it's represented there, whereas in distributional semantics, your rarer words tend to get poor representations that don't really line up with anything at all just because they're undertrained. Their approach to morphology, I would say both of them have different advantages there. In semantic networks, you can clearly separate morphological knowledge from semantic knowledge, but in distributional semantics, the fact that you can just implicitly learn morphology along the way is pretty cool. That's at least true in English. I think this falls apart when you get to morphologically less simple languages like agglutinative languages or languages where it's hard to define exactly what a word is. Distributional semantics has the advantage of being grounded in actual language usage. That's like, you're not just like going off the rails and getting away from the way people actually use language because it's based in data. And semantic networks have the nice advantage that you can look at them and you can explain them. So yeah, the key is why don't we have both? And that's the idea in ConceptNet numberbatch. So this is my whimsically named system built on ConceptNet, where we combine sources of we combine the graph structured knowledge in ConceptNet with sources of distributional semantics to create word vectors that are state of the art. They were state of the art in 2016 when we created them, and they appear to still be state of the art, remarkably. And I'll show you some evidence of that in a bit. But so it's a hybrid system. It's by design is multilingual, and these word vectors are aligned across all the different languages. So text in different languages can get the same vectors, can get vectors you can compare to each other. It's an open source system. It's open data, and we develop it and support it at Luminoso. This is an important starting point for us at Luminoso, and we build a lot of stuff on top of it. So here's what goes into ConceptNet numberbatch. The dark blue nodes on here are data that already exists before we start. The light blue nodes are steps that we apply, and then green is the output. So, for example, we've talked about ConceptNet as a knowledge graph and all the different data sources that go into it. Other data you can get Word2Vec pre-trained on Google News. That's pretty great, especially because you can't actually get the Google News data itself, but you can get what Word2Vec learned from it, so that's knowledge that we should have. Similarly, you can get Glove trained on the common crawl of a whole ton of text from the web. Something we added to improve the multilingual representation of word vectors is we took the open subtitles data, subtitles of TV shows and movies in dozens of languages. That's incidentally aligned across languages. We used a slightly modified version of fast text that understands the fact that words can be in different languages and understands that this sentence in this language corresponds to this sentence in this language. We use that modified version of fast text to train a multilingual representation on open subtitles. And so then there's a technique for combining a knowledge graph with distributional semantics word vectors, and that technique is called retrofitting by Manal Faruqi. We have an extension of retrofitting that allows us to not just apply it over the vocabulary of the word embeddings, but apply it over particular vocabulary we want to target, which is the vocabulary of ConceptNet plus a few extra words that all the word embeddings say should be there. So we apply this retrofitting process. It's a very straightforward, greedy process that happens to produce really good word embeddings by combining these two kinds of knowledge. So we join these all together into a common vocabulary. So these are all like 300-dimensional vector representations. So the thing we inherently get by joining them together is this 900-dimensional representation that's a little unwieldy to work with, and it's also a little repetitive because there are certain things that we know the same thing from Word2Vec and from Glove, for example. So we apply dimensionality reduction, something we're pretty familiar with doing anyway, to reduce it back down to 300 dimensions. We apply debiasing process. I am very interested in talking about this later. There's a lot of unfortunate prejudice that ends up baked into word embeddings when you get text from the web in general. And so I'll talk about this step in a while. And the result is ConceptNet numberbatch. So what we're competing with here is kind of the empiricist narrative of natural language processing, the idea that if big data isn't working, you're not using enough of it. So this competing idea says, okay, look, you kind of got this extra data from knowledge graphs, but we would have gotten that data. We just needed to. We would have gotten that knowledge. We just needed to put in more text. And if you ask a research group at a large company what's going on in NLP, they're going to give you the empiricist narrative. They're going to say that the most important thing is that you put in absolutely as much data as possible, and that knowledge is kind of an unimportant shortcut. And I want to show an evaluation graph that says that, I think it highlights that knowledge is important. So here's one word vector evaluation. This is the Stanford Rare Words evaluation. It's one of many evaluations where you want to see that the computer is predicting that words are similar to each other in the same way that a person would. And so you're measuring the correlation between what the computer says and what people say. And so the rare words evaluation is interesting because it's a particularly tricky case of these, and it's the one evaluation that pretty much every project like this evaluates on, because there are so many of these, and unfortunately there's no standard for which ones you should evaluate on, but everyone evaluates on this one, so I can graph progress on this over time. So there was Word2Vec, which repopularized word embeddings, but was not doing that great on this evaluation. There's Glove, which did a fair amount better. There's Omer Levy and Yoav Goldberg looking at Word2Vec and Glove and saying, okay, what are we really trying to do here? And making a nice closed form model that got better word embeddings. And if you stick with just data-driven stuff with no knowledge graphs involved, then you're going to get, you could get about as high as that, or you could take fast text's simplified approach, which originally was underperforming. They've recently put some neat features in that get it to do a lot better. But meanwhile, we've got ConceptNet up here, and I think that there is this, qualitative change in the data that you get because you have knowledge.
Are these all using the same amount of data?
Using the same amount of data.
Glove is
Right.
trained on-
It's not really the same amount of data because the data sources are different. So Word2Vec is trained on Google News and Glove is trained on the Common Crawl. Levy and Goldberg was trained on, I think it was like Wikipedia plus a news corpus. And yeah, fast text originally was using just Wikipedia. One thing they did when they ramped up their accuracy a lot was that they added the Common Crawl. And ConceptNet.
Total that the higher dots are based on larger data.
That is true, and yet the thing I want to observe is that fast text could have all the data that we have, and they're choosing not to use it because they. I'd say that it's a competitive advantage as a large research group to have a method that its benefit comes simply from more data. And so, like if you just use ConceptNet as a source of raw text, I think it wouldn't make this difference. That the difference here is not just the data, it's the fact that there's representation involved. But that is a good point. It would be an interesting thing to like graph accuracy versus like gigabytes of data that went in. But the amount of data in so the Common Crawl is I think like a terabyte or so, and the amount of data in ConceptNet is a few gigabytes. So anyway, that's our story here, is that we want to put common sense back in word embeddings. And so this isn't just about the numbers. It's also about what you can do with the data. That instead of just having these arbitrary mathematical objects that we can compare with each other, we want to be able to take this very effective representation of word embeddings, and we want to be able to reconnect it to ground truth facts. Now, one argument for empiricism here is, what about domain-specific tasks? We've trained on all this domain general data, but a lot of people have NLP they want to do in a particular domain. And so the appeal of an entirely data-driven model is that you can just repeat that process on your different data. And you can't repeat the construction of ConceptNet on different data very easily. Our observation there is that when you want to repeat this process, the data you want to apply it to is probably a lot smaller than the Common Crawl. You don't have a terabyte of text. And what we want to create here is a reusable foundation of common sense so that you have what you've learned from a whole lot of general data, and then you can use a little bit of specific data to specialize it. And that's the domain-specific transfer learning process that we kind of built Luminoso around. The idea that our customers, who are enterprise groups, have a particular data set that they want to understand. And so we can put in that text, we can put it through our many-step NLP pipeline and extract distributional semantics from that data. And then we combine it with the general knowledge that we have in ConceptNet and in ConceptNet numberbatch. And through our transfer learning process, which I don't want this talk to be all about Luminoso, but we've got a process that combines those to get word vector representation that is specific to that domain, and that allows that representation to be learned from a lot less data than if you were just trying to take the text and go straight to word vectors. And so at Luminoso, we can do all kinds of interesting stuff with this. We can make a word cloud that's more informative than your usual word cloud because location means something. We can identify topics and group those together. We can find snippets that are relevant to these different topics. So here's a fun data set. We looked up reviews of a particular horse head mask being sold on Amazon. You can find different topics like, funny joke, you can find people complaining about the smell. You can find everybody making the same joke about how it's a Sarah Jessica Parker mask. This is the kind of thing that the kind of visualization you can get, and that's one of the things that we do at Luminoso. But to return to ConceptNet, once again, this isn't just about the evaluation numbers, but when I make a claim like knowledge matters, I like to be able to back it up. And so we entered ConceptNet into the SemEval competition last year in a task that was about recognizing similarity and relatedness, a lot like that rare words task, but this time the task was in 5 languages. It's SemEval, so it's on unseen data. Everyone's submitting their results at the same time, and the gold standard is not known. Everybody gets their evaluation results at the same time. And it was a pretty well-designed data set. It involved a lot of, a combination of common words and named entities. It involved single words and multi-word expressions. And it had one subtask that's about comparing words in the same language, and another subtask that's about comparing words in different languages. And this subtask made us particularly excited because that's what our representation was kind of specialized for. And so here's a graph of performance on the within languages task. So we are the blue line. The light blue around it is the margin of error. And we did the best on 4 of the languages and the best average overall. Farsi is not a language we've put that much into, and there were 2 systems that had very Farsi-specific data that beat us on that. And on the cross-lingual task, even in Farsi, in all the language combinations, we were far above the rest. So enough about comparing word similarity. Let's do something more exciting with these word vectors. One thing you can do with word vectors is you can make analogies. I'm not even going to give the analogy about like genders of royalty that you've probably seen 100 times. But the idea is that if you have words in your vector space, you can find differences between these words, and if you have parallel differences, then that represents an analogy. Like the idea that veer is going off course and digress is going off of the subject. And so the differences between these should be similar to each other. One thing that we added to that is that it's not just about finding parallel lines. There are a whole lot of ways in a 300-dimensional vector space for things to be parallel and to still not quite make good analogies. We added another constraint, which is that the remaining sides should also be roughly parallel to each other. That a really good analogy is one where you can swap the 2 inner terms and it still makes a good analogy. Basically, we're looking for parallelograms in our vector space, and that's what looks like a good analogy to us. And so another analogy is that, when something is, you can fix something being plain by decorating it. You can fix something being raw by cooking it. And so there are some pretty complex relations being represented in these vector space differences, often ones that we have no explicit representation of. Yes?
So is the point about parallelograms just sort of to say that the norm of your vectors is also meaningful? Or am I missing something?
Is it about the norm? It's like...
the vectors are the same length.
Right. So Yeah, in our vector space, when we're comparing vectors to each other, we generally normalize them to unit vectors, like just like right before we do anything with them anyway. So it's not about the length of the vectors. Let's see. I think it's more about like in a good solid analogy, the distinction you're making between the two things on the same side should also be interesting. And you should be making a comparable distinction on the other side.
So you're saying in this example that the relationship between plain and raw should be somehow related to the relationship between decorated and cook?
Yes, and it's a very hard one to express like what that actually is as a relation. But there are certain analogies that that makes a lot of sense that you can actually like say what that relation is. And when we added these constraints, we got better performance on analogies across the board. So, yeah,
that constraint is weaker presumably than the solid line. Right?
Yeah, yeah. But so here's our data set that we wanted to evaluate these on. Like there's Mikolov's analogy data set out there that was published with Word2Vec. These are very easy analogies, and I'm pretty sure that data set is maxed out. But one data set that's definitely not maxed out is solving SAT analogy questions, and this has been the kind of the standard for evaluating analogies on your word vectors or on your word representations, whatever they are, going back to Peter Turney's work starting in 2005. And so, here's one that might take a bit of thought. Remuneration is to labor as, and you got to pick one of these 5 possibilities. And so the relation being expressed here is that B is what, so A is what you get for B. And so the answer is trophy is to victory. And so using this parallelogram constraint over ConceptNet numberbatch, we can get 56.1% of these questions right. And for comparison, that's a little better than than Peter Turney's best previous system that works with comparable data. And it's getting close to kind of a mediocre high schooler taking the SAT test. I think it's possible to do a lot better than average human performance here. We should not see average human performance as a ceiling, but it's a nice thing to be able to compare to. Turney also has a system that is that also scored the same score, 56.1%, way back in 2006. It's a very different system because it would actually search AltaVista for all possible pairs of words that you could be looking for. You can't do that anymore. Like there's no, as far as I know, there's no AltaVista anymore. If you do that on Google, you get captured in the first like 2 minutes. And it had to do like 9 days of web searching to actually complete the test. So that's a bit of a different comparison. But SuperSim is a system working with pretty much the same input as ours. So that's another thing you can do with word vectors. Here's a thing that came from this year's STEM eval that we participated in. The idea of, yes? Yeah, that's a good question. The fact that like this, so LRA was the name of Turney's system from 2006, and the fact that that result couldn't be replicated in the decade after it, I think, just highlights the massive amounts of data that it requires. And just your ability to slowly, sparsely query this massive amounts of data. It is a very interesting question whether someone who has access to that massive amount of data anyway can replicate that. That is a good question. So another thing you can do with word vectors, and so this is a STEM eval task from this year that I think the task description is highlighting a weakness in distributional semantics. The idea that if you look up your word vector for Americano, you can say, okay, well, it's something that's similar to cappuccino and espresso, but you don't really know what Americano is unless you can say the differences between these things. And that was the idea of the STEM eval task that we entered. So you get a pair of words like frog and snail, and you get an attribute that is, you're supposed to find attributes that describe the first word and not the second. So animal would be a negative example because it describes both. Key would be a negative example because it has really nothing to do with either. But legs is a positive example in that a frog has legs and a snail does not. And so we have not seen the full results from this yet. This just happened. We have seen our results from it, and we've seen a comparison of scores. So one thing I can show is our ablation analysis of, we put in a combination of different features and which are the features that mattered here. So our best system was the one using all 5 of these features. We used vector similarity over ConceptNet numberbatch. We used a fancier inference method that I'm going to talk about in a moment using semantic matching energy. We also looked up words like the definition, like how Wikipedia introduces these words. That can tell you things about attributes. We looked up the words directly in WordNet, including the glosses of the word. And we looked for words that co-occur particularly often on Google Books, in the Google Books n-grams data. So these different dots are showing the different combinations of features that we used. Generally, as you add more features, of course, you get better. We can also look at the individual features. Notice that ConceptNet numberbatch on its own actually turns out to have done quite well, especially on the test data. I think the test data was a little bit easier than the validation data, which the test data was the data that we couldn't see until we submitted. And so our best system got about 73.7% on the test set. The leaderboard says the highest, it says that that's about like where most of the pack is. There's one system that gets 75%, which is like just barely overlapping margin of error with that. And I'm very curious what that system did. But again, these results aren't all out yet. But it's interesting that you can add all these different features, but also it's like the fact that in a lot of cases, just the ConceptNet numberbatch alone is enough that we thought we had to add this explicit model of how words are related to be able to say, okay, this is an attribute of this word and this is not. And it could be that just differences in these ConceptNet numberbatch vectors are enough to represent most of those. But let's talk about this more complicated model because there's other stuff that we're doing with it. So we want to be able to infer not just that 2 terms are related using ConceptNet, but how they're related. So we want to have a model that outputs not just these scalar similarities between things. We want to have, so not just term embeddings that we compare to each other, but we also want to have relation embeddings. We want to say, we want to be able to predict relations between things. And there are many possible models for this. The one that we chose is Xavier Glorow's semantic matching energy. And the appeal of this model is that it can be used in multiple ways. And so this is a model, you just define you define what you want your embeddings to do. You want it to predict true statements more than false statements. You make a loss function out of that. You can train that for like several days using PyTorch. But again, the model doesn't care what direction these arrows go in. You've just got this tensor, this 3-dimensional tensor, indicating relations between 2 term embeddings and relation embeddings. So if we run it this way, we're putting in 2 terms, and it's telling us how they're related. If we swap a couple of arrows around, we're putting in a term and a relation, and it's telling us terms that satisfy that. That's a question answering thing. Like you can say, like, what kind of thing is a chair? What is a chair used for? Where would a chair be located? And it's outputting, it's ranking candidate answers. And this is useful. You can use this for augmenting a knowledge base. You can use this for making topic models that are more specific. Like maybe you want a model that is not just like, that doesn't just mix up like types of vehicle and parts of vehicles, but that has those as different topics.
So I'm just curious, if you were to run this over ConceptNet data, how much information do you lose?
How much information do you
So if
lose?
you have a triple in ConceptNet,
Yeah.
then you ask the subjects and predicates and ask what the argument is.
Yeah.
Does this score perfectly?
Right. Oh, so that's, yeah, it's interesting. So like if you, like how much is it memorizing from ConceptNet, and what numbers do you get when you put a ConceptNet relation in? Yes.
Have you lost some
Yes. You do lose information, but I am very interested in the information being lost. And let's talk about coherence checking. So let's put all the arrows inward. So now we're putting in the two terms and the relation. We're getting out just a number. And this number is a confidence value, and it's basically telling you how much is this statement supported by all the other statements that you have. And so my observation is that about like 99% of the statements in ConceptNet come out with positive numbers here. But the 1% that don't are really interesting because they are showing us like errors in ConceptNet, sources of large ambiguities, like by the fact that we don't really have word sense disambiguation, or they can show us missing data. And so what I did here was I ran all of ConceptNet through it. So this is like, I put in like the first 10,000 or so edges that were in my shuffled data file and pulled out the lowest scoring statements there. And we can see different kinds of bugs here. So we can find human error, we can find like parsing errors. One thing I notice is that one of our Wiktionary parsing processes is designed to discover the fact that like word A is derived from word B. And that usually works, but apparently there's some Wiktionary template that's confusing it and it's getting it backwards. The model has an idea that this is a relation that goes in this particular direction, and if you see the opposite of that, then that looks wrong, and it's telling us that. Some of this is the fact that we got this games with a purpose data, and that data isn't perfect. People would often say like things like wind is the opposite of air or something, which is not true. It's probably that their partner kept saying things that were too related to air, and they're trying to clue wind, and they're like, no, not that. And so it's an interesting artifact of that kind of data. And I looked up some of these Chinese things, and they are sometimes slightly dubious assertions. Like one thing that it particularly doesn't believe is like someone was trying to make a distinction between record and tape, the system's like, well, tape is very related to record, and so that seems wrong. So there's kind of confusion on both sides there, but definitely an interesting case of where the knowledge in ConceptNet isn't quite holding up. Yeah.
Could some of the could errors be introduced by the multilingual nature of it? Like, for example, you could imagine that error in one language would mean still error.
Mm-hmm.
Would mean like moving.
Yeah.
And they would be on.
Yeah, that's definitely interesting because so there's errors introduced, or there's kind of there's fuzziness for one thing introduced by the fact that that we don't have word sense distinguishing information really. We have like input data that can distinguish word senses, but I will talk about why we don't have quite enough. So there's fuzziness that comes from that, and the fact that like two things can be the same word in one language and different words in a different language. You can also turn that around and say, okay, this is actually an advantage of the multilingual representation, that you can tell that you've got this word that's ambiguous because of the fact that it's translated to very different things in different languages, and because of the fact that this word in one language is bridging these two very different domains. So that's information that we could be using, and I want to talk about that in a moment. There's the big question of like, how do you represent differences in word senses? And maybe one way to represent that is by translating it to another language. So another thing I want to talk about word vectors is you have to be a little careful about what they learn. There's been a lot of news about this recently, including this splashy science article by Eileen Kauskan and et al. About the fact that machines are learning some pretty unfortunate things from people. I'm running on time. Yes. Sorry. You've put in all this data into your word vectors. It's read the news, including all of the existing past biases of our society. It's read the web, including some pretty unfortunate stuff on the web. And so I started noticing this in this was coming through in ConceptNet, and I needed to do something about this. And here's an excerpt from a blog post I wrote that's been reasonably widely quoted here. So yeah, like particular things that show up across many different word embeddings is that it ends up representing words for women and associating them with more subordinate roles. It ends up associating words for minorities with negative terms. This is a bug. This is something we need to fix. And so this is something that I've been working on in ConceptNet. We want to be able to measure these stereotypes and prejudices, and we want to be able to reduce them. And we want to do it in such a way that doesn't remove the accuracy of the data for other purposes. And we've got some progress on that. There's a ton more to be done. There's a ton more to be measured. But generally what I'm doing is following an idea from Tolga Bolakbasi and Kaiwei Cheng at Microsoft Research. They're kind of leaders in this area. They published an idea of how to remove bias from word embeddings that was a bit too computationally intensive at the time. We implemented a simpler version of it. They've now presented a simpler version of it that's kind of a lot like ours. But the idea is that now you can, here's another place where knowledge helps. Do a mechanical Turk thing. Show people a bunch of analogies that your word vectors can make that are designed to pick out gender differences, for example, and ask them, is this appropriate? And you can get people to generally agree on what's appropriate and what's not. And now we can plot words on whether the word vectors are being associated more with one gender than the other, and on how appropriate that distinction is according to people on Mechanical Turk. And the transformation we want to do to our word vectors is to take everything that's below a certain level of appropriateness and just subtract out the gender part. And so this is on test data that was not the input data that we used for subtracting out that axis. And most things that we were trying to subtract out the gender component of ended up pretty much on that axis. So that's, again, we managed to quite effectively mitigate gender bias. Dealing with other kinds of distinctions between people, there are so many ways to distinguish people. There's a lot more to be done, and there's a lot more to figure out about what is appropriate and reasonable to do. But one other thing I want to measure is that people should not have very different sentiments associated with them just because they have different names. There are many production NLP systems out there running that if you give them a black sounding name, will say that it sounds more negative than a white sounding name, and that's a big problem. And so this is before debiasing in ConceptNet. This is highlighting that that's a problem. And after our debiasing process, its comparisons between people are a lot more equitable. So let's talk about some next steps, although I realize I'm running low on time. I want to use ConceptNet to aid explainability. There's been great progress recently on explaining AI classifiers that used to be black boxes by finding simple explanations of their results based on linear differences in features, for example, using Ribeiro-Edel's LIME. And that's really cool, but what if your input features are word embeddings? How do you make that explainable? And so my hope is that we can make word embeddings explainable by tracing the features back to ConceptNet assertions. Talked about word senses. Actually being able to represent word senses in ConceptNet is daunting, and the biggest thing to figure out is there is no unified inventory of word senses. If you ask a question, how many senses are there of the word run? If you ask WordNet, it gives you 57. If you ask the English Wiktionary, it gives you 95 different senses. If you take kind of an outside view and ask the German Wiktionary to define the English word run, it gives you 4 senses. The answer is probably more than 4. The useful answer is probably more than 4 and probably less than 57. But really this highlights that we probably need a continuous vector space with kind of clusters to be able to represent the idea of word senses. I want to be able to do more with debiasing. Bolakbasi and Cheng et al. have done more recently. I watched the presentation they just gave at the Fairness and Transparency Conference. We agree on the first step that needs to be done. They've done another step, but they've only applied it to gender. Can we implement their next step while debiasing multiple attributes? The next step is about the fact that once you've removed the inappropriate distinctions, what if it's just moving all the bias and hiding it in the appropriate distinctions? What if instead of learning a difference between all the male things and all the female things, what if it's learning a difference between, well, here's a difference between mothers and fathers and between aunts and uncles and stuff like that? What if it hides it in the distinctions it's allowed to make. So there's another step that needs to be done. And another interesting question is, does debiasing survive in downstream applications of these word vectors? I have seen that debiasing does survive when you make analogies using these word vectors. On the other hand, if you want to make a more compact, dimensionality reduced version of these word vectors, one thing that appears to happen is that the sum of the bias comes back. So being able to examine that and being able to measure that is pretty important. So we've got this process for inferring relations over ConceptNet. We've got this process that we use particularly at Luminoso for transferring knowledge into a domain. Can we compose these representations? Can we use this process to infer relations about a customer-specific domain? That would be cool. But another thing I want to do with ConceptNet is just make more fun things possible with it. So there's this site called robotmindmeld.com. It's based on an improv game where two people try to say the same word. And it was made by someone named Alex Liu, who I don't know. He's a high school teacher. He just got the ConceptNet data and made this site out of it, and it's awesome. And I want to be able to enable more of this kind of thing. So here's an example of gameplay of it. I said the word radio at the same time it said the word worms, and then we took that information and tried to say a word that was related to both of them, and after 5 steps, then the computer and I had converged on the same word, and this is using ConceptNet numberbatch. An example of a fun thing I would like to do, there's a board game called Codenames that's about cluing multiple words on a board with single word clues. I believe that we'd be able to use ConceptNet to make an AI that can either give clues or receive clues in the game of Codenames, and I think that could be a very inspiring example of how to use knowledge-based NLP. So if you want more information on all this stuff, here are a few pointers. There's my blog, which has updates on ConceptNet and on related open source tools. There's the browsable interface, conceptnet.io. There's the API, which you can build things on top of in this pretty reasonable JSON linked data format. If you want information about what we actually do with this from a business purpose, there's luminoso.com. Again, I didn't come here to pitch Luminoso, but it's what I actually spend most of my time on. And yeah, so I'll wrap up here. Thank you to Catherine, who started all of this, to my coworker Joanna, who helps make all this stuff happen, to Joshua Chin, who was the first to make word embeddings that outperformed Levy and Goldberg's, and that was a really surprising and exciting moment when it happened. Here are those links again. And I have time for very brief questions.
Mm-hmm.